The shells all end up in a storage yard outside Cambridge on the eastern shore, where oyster larvae are raised by the billions, which are then released onto recycled shells that take a year to prepare.
When Florida dumped over 500,000 tons of oyster shells into the Gulf of Mexico between 2007 and 2024, people didn't take it lightly, but nature had its plans. At first, the shells were just piles of white on the sand, lifeless and silent. But over time, what began to form there defies logic. Something ordinary had sparked something extraordinary, and science couldn't seem to find the perfect explanation for it. Could discarded shells really rebuild entire ecosystems? How did nature turn human leftovers into a living reef? Join us as we uncover the unbelievable story beneath the waves. The ocean experiment nobody believed would work. When scientists first returned to the offshore sites near Cedar Key, Florida, they expected failure. They had spent countless hours planning, coordinating logistics, and organizing the collection of over 500,000 tons of oyster shells from restaurants and seafood processing plants across the state. From 2007 to 2024, these shells had been carefully transported and deposited into the Gulf of Mexico. To the naked eye, it had looked like an expensive, controversial experiment destined to fail. Yet what they discovered defied expectation. Clusters of marine life were forming in places that had been completely barren. Tiny fish darting through piles of shells, barnacles beginning to colonize the surfaces, and subtle movements of creatures using the calcium white mounds as shelter. What was supposed to be lifeless debris was beginning to hum with the first signs of a living reef. The project had been controversial from the very beginning. Environmental groups had protested, labeling the initiative ocean dumping disguised as conservation. They argued that dumping 500,000 tons of waste into the Gulf would destroy the ecosystem rather than restore it. Local fishermen, who had long relied on the Gulf's fragile ecosystems, feared habitat destruction, sediment burial, and the disruption of centuries-old fishing grounds. Critics warned that the project was reckless and wasteful, predicting that decades of ecological imbalance would follow. Despite these warnings, the Florida Fish and Wildlife Conservation Commission pressed on, believing that the discarded shells, otherwise destined for landfills, could serve as a foundation for a new generation of oyster reefs. For the first 18 months after the initial deposition, monitoring teams observed a mystery unfolding. Life was returning to the seafloor much faster than anyone had anticipated. Typically, artificial reef projects, such as sunken ships or concrete reef balls, take 2 to 3 years before they begin showing significant biological colonization. These oyster shells, however, had already drawn microscopic organisms, small invertebrates, and the first hints of oyster spat within a year. Marine biologists were astonished. The shells were acting as more than a physical substrate. They were functioning as biological triggers. At first, the shell piles looked exactly as critics had feared. Dead oyster shells sat in mounds across the sandy bottom, stark and uninviting, almost like calcium debris dumped carelessly. There were no fish, no visible signs of coral, and no dramatic bursts of life. Yet beneath the surface, subtle processes were unfolding. These shells were attracting microscopic organisms in ways that sand or mud could not. Bacteria and microalgae began colonizing the shells, creating the base of an entirely new food web. What seemed inert was quietly transforming the local environment, preparing it for life on a much larger scale. The scale of the operation added another layer of intrigue. Over 500,000 tons of shells had been deposited across specific offshore locations. Every ton of shell represented years of ecological waste avoided from landfills. Yet no one predicted the rate or scale at which these shells would jumpstart life. Monitoring teams began noticing unusual acceleration in colonization. Structures that normally required years to support marine life were now fostering it in mere months. The oyster shell's chemical composition, aragonite, a form of calcium carbonate, was partially dissolving in seawater, subtly altering water chemistry. This created tiny alkaline zones that encouraged barnacles, tube worms, and other calcifying organisms to attach, grow, and multiply. In essence, the shells were fertilizing themselves. Even the fishermen who had opposed the project were forced to acknowledge the results. Areas that were once barren and feared destroyed were beginning to show fish activity. Schools of small reef fish were spotted hiding among the shell mounds. The mystery was no longer hypothetical. It was tangible, measurable, and undeniable. A project once dismissed as ocean dumping had unexpectedly become the starting point for something far greater. The question, however, remained: what had truly happened in those first invisible months when life seemed absent? How could hundreds of thousands of tons of discarded shells, appearing lifeless, trigger a cascade of biological processes powerful enough to restore entire ecosystems? Scientists and skeptics alike were left staring at the mounds in awe, trying to comprehend what had quietly unfolded beneath the surface. The answer was about to emerge, but it began at the microscopic scale, hidden from view. But if piles of discarded shells could suddenly turn into thriving, living reefs, what exactly was happening beneath the water during those invisible, critical months that no one could see? The invisible phase, microlife that rebuilt an ecosystem. For the first 6 months after the oyster shells were deposited offshore near Cedar Key, the Gulf of Mexico looked, to any casual observer, exactly as the critics had predicted: barren, pale, and lifeless. Mounds of discarded shells rested on soft, sandy seafloor with no apparent signs of life. But beneath the surface, in a world invisible to the naked eye, a remarkable transformation was quietly taking place. This was the invisible phase, the stage in which the tiniest organisms laid the foundation for one of the fastest and most successful ecosystem restorations ever recorded. The pioneers were microscopic bacteria. They were the first to sense the unique opportunity presented by the oyster shells, adhering to the calcium carbonate surfaces and forming biofilms. These films were not random, haphazard patches of bacteria. They were structured, living carpets that created a microhabitat capable of supporting further colonization. Within weeks, diatoms and other microscopic algae began to appear, feeding off nutrients in the water and forming the base of a simple but critical food web. In this microscopic arena, life was establishing itself where previously there had been none. Sandy seabeds, which typically cannot sustain reef ecosystems, offered no surfaces for attachment and no protective chemical microzones. The oyster shells were the critical difference, acting as both shelter and chemical incubator. Chemistry played an equally important role. The shells were composed primarily of aragonite, a form of calcium carbonate that dissolves slightly in seawater. As the shells slowly released calcium ions, they altered the surrounding water chemistry, creating localized alkaline microzones. These changes accelerated the growth of calcifying organisms, including barnacles, tube worms, and, crucially, juvenile oysters. In this way, the shells were not just passive structures. They were active participants in the ecosystem, fertilizing themselves and ensuring that the early colonizers thrived. The rate at which this microscopic colonization occurred stunned scientists. Where artificial reefs made of concrete or steel typically take 2 to 3 years before significant life establishes itself, the oyster shells achieved the same result in a mere 6 months. Although this initial phase was invisible to human eyes, it was essential to the ecological explosion that would follow. Without the bacteria, algae, and early calcifiers creating this microscopic framework, nothing larger could attach, survive, or grow. This was the hidden scaffolding of life, quietly constructing the blueprint of a fully functioning reef ecosystem. It was a reminder that, in nature, the smallest elements often wield the greatest power, unseen but absolutely vital. Marine biologists began documenting subtle yet significant signs that the ecosystem was building momentum. Microscopic organisms were attracting slightly larger creatures, including tiny crustaceans and larval mollusks, which fed on the biofilms and algae. These early settlers, in turn, attracted juvenile fish, searching for food and shelter. The initial oyster shells were no longer just inert debris. They had become the stage for the first interactions of a complex, living community. By the end of the first half-year, the oyster shells had transformed chemically and biologically. Their surfaces were coated in layers of biofilm and microalgae, a faint shimmer detectable only under close observation. This stage, although invisible and seemingly unimpressive, was the critical turning point. It established a living base that would support the next wave of colonization, the oysters themselves. Without this invisible phase, the thousands of oysters that would eventually settle could not have survived, and the reef would have remained lifeless. Perhaps the most remarkable part of this stage was the speed of change. In typical artificial reef development, the time lag between construction and ecological productivity is measured in years, sometimes decades. Here, nature had accelerated its processes, responding almost immediately to the chemical and structural cues provided by the shells. The early colonization formed a self-reinforcing feedback loop. Bacterial films supported microalgae. Microalgae fed tiny grazers, and those grazers encouraged further biofilm growth. Every microscopic interaction was a step toward a larger, living ecosystem that no human hand could fully replicate. As the scientists watched these invisible processes unfold, the anticipation grew. They knew the next stage, the arrival of juvenile oysters, or spat, would be the real test. Would the oysters find these chemically and biologically prepared surfaces? Would they settle, grow, and reproduce in a way that could sustain the new reef? The seeds of an ecological miracle had been planted, but the story was only just beginning. Once the microscopic world had firmly established itself, the next phase would unfold with dramatic speed. The oysters themselves were about to arrive, and what they did next would completely redefine how we think about restoration and the power hidden within discarded shells. The return of the reef builders. Oysters are far more than a seafood delicacy. They are ecosystem engineers. To thrive, these creatures require hard surfaces on which to attach. In the wild, oyster larvae, or spat, drift with the currents until they find suitable substrate, usually the shells of older oysters. Without this hard surface, they cannot establish themselves, and their life cycle is interrupted. For decades, Florida's Gulf Coast had experienced the collapse of natural oyster reefs. Overharvesting, pollution, and coastal development had decimated what was once a thriving network of reefs, stretching across hundreds of square miles. By the early 21st century, natural reefs were scarce, leaving oyster larvae with virtually nowhere to settle. When Florida began dumping the discarded oyster shells offshore, it was initially viewed as a simple disposal strategy. Critics labeled it waste dumping, but the shells solved a critical ecological bottleneck almost immediately. Each shell provided an ideal landing site for the drifting spat, concentrated in a way that mimicked natural reef clusters, but on a much faster timeline. Within the first year, biologists documented juvenile oysters attaching to the shells in remarkable numbers. The larvae were finding the substrate, settling, and beginning to grow where only sand and silt had existed before. By the end of the second year, those juveniles had matured into adult oysters, capable of reproducing. They began producing their own larvae, creating a self-sustaining cycle that no one had anticipated would occur so quickly. The oysters were no longer just taking refuge on the dumped shells. They were actively contributing to reef growth. This marked a pivotal point in the project. Human intervention had created the initial conditions, but nature had taken over. By the third year, the transformation was profound. The shell deposits had evolved into functioning oyster reef systems, dense and productive, comparable to or exceeding historical natural reefs in the same region. Observations revealed astonishing density, an average of 847 oysters per cubic meter of deposited shells. Nearby sandy bottom areas, devoid of substrate, supported virtually no oysters at all. The reefs were no longer dependent on additional human input. Oysters were reproducing, dying, and providing new shells for subsequent generations. Vertical and horizontal growth occurred naturally, and the reefs began expanding outward, their structural complexity increasing with each cycle. The process demonstrated something remarkable about ecological restoration. Small, foundational interventions could trigger self-reinforcing natural processes. What had begun as discarded shells became the foundation for thriving ecosystems. Reefs expanded beyond the original deposition sites, gradually rebuilding what had been lost over decades. Scientists noted that the oyster reefs were self-maintaining, regenerating, and, in many cases, growing more robust than the degraded natural reefs they replaced. The shells were no longer just substrate. They were the beginning of an entire ecosystem engineered by nature itself. By this stage, human intervention had transitioned from active creation to passive observation. Researchers monitored the reefs, documenting growth, oyster densities, and reproductive success, but the oysters were performing the hard work themselves. This stage underscored the elegance of working with natural systems rather than imposing artificial structures. The dumped shells had acted as catalysts, but the real reef builders were the oysters, quietly reconstructing the Gulf Coast habitat in ways that human engineers could never have fully predicted. But oysters weren't the only creatures responding to the new habitat. Soon, the entire food chain started shifting, and the transformation of the Gulf ecosystem was only beginning. When the fish arrived, everything changed. Once the oysters had established themselves, the reefs began attracting other marine life at astonishing rates. Juvenile fish were among the first to respond, seeking shelter within the complex three-dimensional structures of shells and growing oyster clusters. Small fish found refuge from predators in the nooks and crannies of the reefs, creating localized safe zones that allowed populations to grow. Within 2 years, surveys indicated dramatic increases in both fish species diversity and population density around the reef sites. Where soft sandy bottom had once supported only sparse marine life, these reefs became bustling undersea neighborhoods. Some of the most notable arrivals were economically important sport fish. Redfish, a prized target for anglers, were observed using the reefs as nurseries. Juvenile redfish hid among the shells, feeding on small crustaceans and algae while avoiding predation. Sheephead, a species that feeds primarily on barnacles and other reef-dwelling organisms, also proliferated. Scientists conducted systematic fish surveys, recording biomass increases of more than 340% compared to control sites. Species diversity had jumped by 280%, highlighting the reef's capacity to support entire food webs rather than simply concentrating existing fish. The ecological changes quickly translated into economic benefits. Charter fishing captains who had initially opposed the shell deposition began requesting new reef sites near popular fishing grounds. Areas once feared destroyed were now prime fishing locations. Tourists, recreational anglers, and commercial operators alike recognized the surge in marine life, and local economies began benefiting from increased fishing activity. Hotels, bait shops, and charter services all saw measurable improvements in revenue, tied directly to the presence of these restored reefs. What began as a controversial ecological experiment had become a critical economic asset. Beyond the immediate economic impacts, the reefs also transformed ecological interactions. Predators, such as larger fish, octopuses, and even sea turtles, began frequenting the reef sites, drawn by the abundance of prey. Each arrival reinforced the food chain, creating a cascading effect that improved the overall resilience and stability of the ecosystem. The reefs no longer served solely as oyster habitats. They were functioning, integrated marine ecosystems that mirrored or exceeded the complexity of natural reefs. The pace of change was astonishing. Within a few short years, what had been barren sandbars became thriving, productive reefs teeming with life. The initial deposits of discarded oyster shells had sparked a chain reaction that affected every trophic level, from microscopic algae and larval invertebrates to large predatory fish. Scientists documented that these reefs were not just aggregating existing species, they were producing life, supporting natural recruitment, and sustaining populations that had been struggling to survive along Florida's Gulf Coast for decades. Yet fish were only part of the story, because something even larger was beginning to change the water itself, and the transformation extended far beyond the reefs into the very currents and clarity of the Gulf. The billion-gallon cleaning machines beneath the waves. Oysters are not just remarkable for their role in building reefs, they are natural water filtration machines. Each adult oyster can filter anywhere from 30 to 50 gallons of seawater daily, drawing in suspended particles, algae, bacteria, and excess nutrients. Alone, this may seem modest, but when multiplied across the thousands, then hundreds of thousands of oysters thriving on the shell reefs, the cumulative effect becomes staggering. Entire reef systems were now filtering billions of gallons of water each day, performing the work of industrial-scale water treatment, yet powered purely by nature. The ecological implications were profound. Nitrogen and phosphorus, two of the most harmful components of agricultural and urban runoff, were being removed from the Gulf's waters at unprecedented rates. Excess nutrients often lead to harmful algal blooms, which can suffocate marine life and cloud water. But on these restored reefs, water clarity improved noticeably within just a few years. Dissolved oxygen levels rose, creating a healthier environment for fish, crabs, and other invertebrates. Marine biologists conducting water quality monitoring observed measurable improvements, not just at the immediate reef sites, but radiating outward, affecting surrounding seagrass beds and adjacent ecosystems. Seagrass, a critical habitat for juvenile fish, manatees, and sea turtles, began expanding into areas previously too murky for survival. The positive feedback loop was unmistakable. Oysters filtered water, making it clearer. Clearer water allowed sunlight to reach deeper, enabling seagrass growth. Seagrass in turn stabilized sediment, reduced turbidity, and provided more habitat for marine life. The reef system was no longer just a series of oyster clusters. It was a self-reinforcing ecological engine, improving both biodiversity and water quality simultaneously. The speed and scale of these changes surprised even veteran marine scientists. In less than a decade, areas that had been considered biologically dead or severely degraded were now thriving. Oysters were performing ecological services that humans would have needed to replicate at tremendous financial cost. Researchers estimated that the 500,000 tons of shells deposited offshore between 2007 and 2024 were generating ecological benefits worth tens of millions of dollars, purely through water filtration, seagrass restoration, and habitat creation. The Florida oyster restoration story did not remain unique for long. Inspired by these results, other regions began experimenting with similar programs. In New York Harbor, for instance, the Billion Oyster Project had repurposed millions of discarded restaurant shells to rebuild reefs in previously polluted waters. There, oysters filtered water, improved conditions for seagrass beds, and encouraged marine life to return to areas once written off as biologically dead. The concept was simple yet revolutionary. Give nature the substrate and conditions it needs, and it will perform miracles on a massive scale. In Florida, the combination of physical reef structure and the filtration abilities of oysters had created an undersea water treatment system that was entirely self-sustaining. Unlike mechanical filtration systems, the oysters required no electricity, no maintenance, and no chemical inputs. What humans had once considered waste, discarded oyster shells, had become one of the most efficient natural cleaning systems on the planet. This quiet transformation under the waves was reshaping not only marine habitats, but also the economic and ecological potential of Florida's coastal waters. Cleaner water and growing reefs were impressive, but no one expected these shell structures to influence hurricanes, altering storms' impact on coastlines in ways that would redefine coastal protection. The hurricane test. No one planned. In September of 2017, Hurricane Irma, a Category 4 storm, barreled toward Florida's Gulf Coast. Scientists and coastal communities braced for disaster. Wind speeds exceeded 150 miles per hour. Waves crashed violently against the shore, and storm surge forecasts predicted widespread flooding and erosion. While much of the coastline was exposed to the full force of the hurricane, the areas adjacent to the restored oyster reefs near Cedar Key told a different story. After the storm passed, coastal assessments revealed that shorelines backed by the oyster reefs had experienced significantly less erosion than areas without reefs. On average, erosion was reduced by 30 to 40%, a dramatic difference when compared to nearby soft sand beaches. The reefs, dense with living oysters and layered shells, had acted as natural barriers, breaking up wave energy before it could reach the shore. The complex, three-dimensional structure of the reefs dissipated force and reduced the height and intensity of incoming waves, protecting both natural habitats and human infrastructure. Property owners and local governments took notice. Estimates suggested that the presence of the shell reefs had prevented nearly $3 million in coastal property damage during Hurricane Irma alone. Considering that the total restoration cost of the reef program over 15 years had been approximately $5 million, the reefs were effectively paying for themselves in order to avoid damage. They provided a tangible return on investment, combining ecological restoration with economic resilience. The science behind this phenomenon was straightforward, yet remarkable. Unlike artificial barriers such as seawalls, the oyster reefs grew with the environment. As oysters reproduced and shells accumulated, reef height and surface area increased, providing progressively stronger protection against waves. In essence, Florida's coastlines were gaining a dynamic living defense system capable of adapting to storms year after year. Unlike concrete or steel, which might crack, erode, or require repair, the reefs were self-repairing and self-reinforcing. The success of the oyster reefs as natural coastal defenses prompted a new perspective in environmental management. Ecologists, engineers, and policymakers began considering reef restoration not only as a tool for habitat recovery, but also as a core component of coastal resilience strategies. What had been dismissed as controversial ocean dumping was now recognized as one of the most cost-effective methods for mitigating storm damage while simultaneously supporting biodiversity, improving water quality, and boosting local fisheries. The transformation was not just ecological, it was philosophical. For decades, environmental management had focused on protecting coastlines with hard infrastructure. Now, the natural processes triggered by discarded oyster shells were demonstrating that conservation could serve multiple purposes simultaneously: ecological restoration, economic benefit, and climate resilience. Florida had unintentionally pioneered a model that blended science, waste management, and ecosystem engineering into a single, highly effective strategy. If oyster shells could protect entire coastlines from hurricanes, improve biodiversity, and enhance water quality, why weren't similar projects already happening everywhere? And what could the next level of innovation look like? The global shift toward shell-based restoration. Florida's unexpected oyster reef success did not remain a local story for long. What began as a controversial experiment near Cedar Key quickly became a blueprint for ecological restoration across the Gulf Coast. By 2015, Alabama had launched oyster shell recycling programs, following Florida's example. Mississippi began its own shell deposition projects 3 years later, and Louisiana, home to the Gulf's largest oyster industry, initiated massive reef-building initiatives. Each program adopted the principle that discarded oyster shells, once considered worthless waste, could be transformed into the foundation for thriving ecosystems. The ripple effect extended far beyond the Gulf Coast. Restaurants across the nation began participating in shell recycling initiatives, collecting discarded oyster shells and sending them to curing yards. These shells were no longer simply landfill material, they were raw building blocks for ecosystem recovery. Volunteers, students, and environmental organizations became essential players in this effort, proving that large-scale ecological projects could harness community engagement alongside scientific expertise. International interest soon followed. Coastal engineers in countries from Canada to Australia studied Florida's model, seeking nature-based solutions to problems traditionally addressed with concrete seawalls and artificial reefs. Traditional artificial reef programs often failed to achieve long-term biodiversity gains. Chips and reef balls could provide physical structure, but they rarely supported self-sustaining ecosystems. Fish aggregated around these structures, but the underlying ecological processes, water filtration, habitat creation, and species reproduction, remained absent. Oyster shell reefs were fundamentally different. They worked with natural processes, recreating the life cycles that had been disrupted by human activity. Climate change adaptation strategies now increasingly incorporate oyster reef restoration. Rising sea levels, stronger storms, and increasing coastal erosion have forced policymakers to look for solutions that combine ecosystem health with human safety. Oyster reefs are proving uniquely capable. Not only do they break wave energy and reduce shoreline erosion, but they also act as carbon stabilization zones. Research indicates that dense oyster reefs sequester organic carbon in their shells and surrounding sediments, trapping greenhouse gases that would otherwise contribute to climate change. This emerging data positions oyster restoration at the intersection of habitat recovery and climate mitigation, a rare combination in environmental management. Beyond their scientific significance, these projects highlight an approach known as circular environmental design. Materials once considered waste Oyster shells, coral fragments, limestone rubble can be repurposed as functional infrastructure that supports life. The concept is elegantly simple. By identifying what nature needs and providing it in ways that humans would have previously discarded, entire ecosystems can be rebuilt with minimal technological intervention. Florida's shell reefs became a case study for this paradigm, demonstrating that ecosystem restoration does not always require massive engineering projects or billions of dollars in funding. The global attention sparked by these programs also encouraged cross-disciplinary research. Marine biologists, environmental economists, and engineers began collaborating to measure ecosystem services, calculate economic returns, and explore the long-term viability of shell-based restoration. But even with global attention growing and replication projects underway, scientists discovered something unexpected. The reefs weren't just surviving, they were expanding on their own, growing in ways that challenged traditional understanding of marine restoration. The living structures that refused to stay still. By the early 2020s, it became clear that Florida's shell reefs were not static creations. The reefs were alive in every sense. Oyster reproduction cycles ensured that each generation laid the groundwork for the next. Larvae, known as spat, attached to existing shells, grew into mature oysters and eventually died, leaving behind new substrate for future generations. This natural process caused reefs to grow both vertically, adding height to mounds, and horizontally, expanding their footprint across the seafloor. In some of the oldest reef sites, scientists documented the reef area doubling since its initial deposition. What had begun as concentrated piles of discarded shells had transformed into sprawling living ecosystems. The reef's structural complexity increased over time, providing habitat for dozens of previously absent species. Crabs, octopuses, sea stars, and even endangered sea turtles returned, finding refuge and abundant food among the dense oyster clusters. Dolphins were observed hunting around the reefs, taking advantage of the thriving fish populations supported by the restored habitat. Biodiversity metrics revealed astounding results. Fish densities approached those of pristine natural limestone reefs, while soft-bottom areas nearby still lagged far behind. The reefs became self-sustaining, continuously building themselves without human intervention. Unlike traditional artificial reefs, which often act as fish aggregators without producing new life, the shell reefs were self-replicating and biologically productive. Each dead oyster contributed to a cycle of life that kept the ecosystem dynamic and resilient. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.